In the Bell work that we just looked at, we solved absolute value equations. Absolute value equations always split into two different equations when you solve them. Absolute value inequalities are always going to split into two different inequalities. All right? So when we're dealing with absolute value inequalities, the concept of what the absolute value is even more important. So what is the absolute value? It's the distance from zero. So if we're talking about the distance from zero being less than something or greater than something, then we're talking about two completely different things. If our distance from zero is less than a number, then our distance from zero is that's going to be a different type of compound inequality. If our distance from zero is greater than something, that's a different kind of inequality. All right, so let's just dive in and look at some important concepts. Absolute value is a number's distance from zero. Yeah. Absolute value equations will nearly always split into two different equations. When do they not split into two different equations? When it's equal to a negative number, it has no solutions. And you have to recognize that at the beginning and not split it into two different equations. And there's one other time that it doesn't split into two equations. If it's equal to 0, there's only one number that has an absolute value of 0, so we don't have to split that one into two equations. And then the third fact here is that absolute value inequalities will always split into a compound inequality.
Do we need to write that?
Yes. Absolute value inequalities will always split into a compound inequality. A compound inequality. Y'all remember compound inequalities? Mm-hmm. What were the two words that we had between compound inequalities? Or. So a compound inequality can either be an or problem, which is a union. It's just where you graph the two things together. All right? They usually ended up looking like something like this, right? Where you have two values and we shade outside, right? That's usually what the graphs ended up looking like, usually. And that's not going to be any different for absolute value inequalities. What was the other kind of compound inequalities? Were ands. And that is the intersection of two sets, and usually it ended up being a solid set between two values. Okay, so we have to know, when absolute value inequalities, we have to know whether we are dealing with an or whether we are dealing with an and. Okay? Big difference, right? They're graphed completely different.
Why is always in quote there? In quotes?
Because it's always in math. It's kind of always in this case means almost all the time. Okay. There's other ways, but you're always safe to split it into two. With equations, you can't always split it into two. All right. Most of the time, nearly always, they split into two. All right? So let's look at an example. First one. Absolute value of x is less than 4.
X is...
No. Just don't try to work ahead. I want to ask you a question here. Absolute value of x is less than 4. Using the definition of absolute value, how would you interpret what this is asking for? So we're looking for every number or any number whose distance from 0 is less than 4.
2.
What would that look like on a number line? How would you graph that? We're going to start kind of looking...
Open circle to the left, right?
Well, to the left of what?
To the left of the 4.
All right, but we can't keep going to the left, right? Because remember, we want our distance to be...
We can go to -3.
No, we can go all the way to -4, but we can't touch it.
Why can't we keep going?
Because if I pick a number over here, -5, and plug that in right there, do I get a true statement? is the absolute value of negative 5 less than 4? No, because negative 5 has a distance from 0 that is equal to 5. And I'm interested in any number whose distance from 0 is less than 4 units. So I'm interested in all the numbers in between those two numbers. Do what?
How would you write it?
Now, yeah, I'm starting graphically because I'm going to show you how to write this. Now, does that graph describe an OR problem or an AND problem?
And
It describes an AND problem, right? So if we have an absolute value that is less than, we're always going to be dealing with an AND problem. Less than AND.
what
Okay?
greater than would be or.
Greater than is OR. Greater. Greater, right? But that's only dealing with absolute values. So the two inequalities that we're looking at here are x is less than 4 and x is greater than negative 4. Flip the symbol, change the sign. Flip the symbol, change the sign. Okay? Now, if we kind of started with the graph on this one, and we'll start the next one on the graph, but the rest of them we're going to kind of do straightforward algebraically, and then we'll use this to graph it. So negative 4 and 4 are the two numbers of interest. We're looking for intersections, so this one less than 4 looks like that. Greater than negative 4 looks like that. The intersection is the parts that are shaded on both graphs. So this is my solution graph. So I've got an algebraic solution and I have a graphical solution. Okay? Does anybody remember what the interval notation answer would look at? You're not going to be tested on this, but what would the interval notation be? Yeah, Wilson?
Infinity 4.
No infinities here.
Um,
This is the set of numbers between negative 4 and positive 4. And we use parentheses for open circles, brackets for closed circles. Okay? So this is what the interval notation, this is the Algebra 2 answer. When you get to Algebra 2, you'll use interval notation just about all the time. Or you would if I was teaching it. All right, letter B. Letter B. Absolute value of x is greater than 7. Now, somebody interpret that for me. What numbers are we talking about there?
The numbers between 7 and negative 7. No,
Okay.
Oh, wait. Oh, it's a greater than. So.
Using the definition of absolute value, yes, Brent, it's going to be an OR problem. Using the definition of absolute value, what are we looking for? Numbers that have a distance from 0 that is greater than 7. We're looking for all the numbers that have a distance from 0 that is greater than 7. What would that look like graphically? The distance has to be more than 7 units away from 0. Seven and negative 7, right? And greater than that, the distance would be over here, yeah? And then negative 7, that would make our distance over here. Now, if you pick any value in these intervals, any value out here, and plug it into that equation for x, you're going to get a true statement. If you pick any value from the inside here, if you pick negative 1, and you plug it into there, what do you get? 1 is greater than 7. That is not part of the solution set. Right? So, now does that look like an AND problem or does that look like an OR problem? OR. And the reason that I want you to see it this way is because you may forget absolute value less than is always AND, greater than is always OR. But you can always think about the distances, right? If the distance is greater than 7, that means we're going out. We're opening away from 0. Our distance is greater than 7. Our distance is opening away. It's getting larger. That's an OR problem. That's what they look like. If the distance is less than 0, that means we're closing in. Our distance is getting shorter. It's closing in. It's restrained. And that's what an AND problem looks like. So thinking about absolute value in terms of what it is extremely important. And we're going to look at some tolerance problems in this context as well. But that's going to come a bit later. Let's look at one that's a little bit more A little bit more difficult. We're kind of adding a step in each one of these examples. Now, what was one of our rules for absolute value problems, equations?
How would you write this fast?
Oh, you know what? We didn't finish that last example, did we? Let's go back to that one. Thank you, Buchanan. We didn't write it. No, I just started with the graph and didn't explain it. So that graph that we had looked something like, let me go back again, something like this, right? 7, -7, open circle shade this way, open circle shade that way. That's x is greater than 7, or x is less than -7. So same thing, you flip the symbol, right? We start with the equation that we're given, x is greater than 7, and then we flip the symbol and change the sign. The same way we did with the less than. Flip the symbol, change the sign. All right? So that's how that would be written. Now, interval notation for this interval over here, this shaded interval on the left, is -infinity to -7. And that's a union of 7 to positive infinity.
Do we write or?
I'm not going to test you that. Do what?
Did you write or instead?
You could write or instead of the union symbol, but generally you use union for that. There is an intersection symbol, but the intersection symbol is kind of not going to be useful for and problems because it's always going to be the intersection, which is going to be a continuous interval, so you can just use one interval instead of two. Wilson?
I thought there were brackets next to the infinity.
No, it can't equal infinity, so it's always going to be a parentheses. You can't get to infinity. All right? So it's an open circle for sure on infinity. All right. Now, in absolute value equations, what did we have to do before we could split the equation into two?
Get rid of the numbers.
You have to get the absolute value part by itself. We have to isolate it. So in the left-hand example here, what would we do?
Subtract 7.4.
Subtract 7.4 from both sides. And that would give us the absolute value of x is less than or equal to 2.4. Is that right? By the way, y'all remind me to talk about Math Olympics today. Absolute value of x is less than or equal to 2.4. Absolute value inequalities will always split into two different inequalities, and they will always be an and or an or. Which one is this? And. Less than is and, greater is or. So this will split into x is less than or equal to 2.4. And, what do we do? Flip the symbol, change the sign. When we did equations, we always changed the sign. We didn't have a symbol to flip. If you flip an equal sign, it's still an equal sign. Right? X is less than or equal to 2.4. And x is greater than or equal to -2.4. What's the graph going to look like of this? Compound inequalities we're always going to graph. 2.4, -2.4. Closed circles, right? Less than or equal to is a closed circle and shade to the left. For and problems, we do our inequalities above. The only thing that makes it to our number line is the actual intersection. Greater than or equal to -2.4 looks like that. Do we have intersection? Yeah, these two graphs cross over each other. Now, the reason I ask you that question is because it's possible for them to have no intersection. It's possible to have no solutions. So don't ever assume that you just shade in between the two numbers. That's a risky assumption to make. You'll get it right about 80% of the time if you do that. We're not 80%ers in here. Okay? We want to be in the 90%ers range. 100%ers. That's right. So you always want to be careful not to assume that because it's an and problem, you just shade between the two numbers. We're going to look at some special cases, and I'm going to show you that and problems can have no solutions. Okay? Or problems would rarely have no solutions, but or problems can be all real numbers. So you need to shade your OR problems as well. All right, so it can end up shading the whole number line. All right, we're not going to work the letter B here because it's quite simple, but what will we have to do first before we can split that into two? Multiply everything by 4. Do we have to flip the symbol when we multiply by 4? No, not at all. Yeah, so if you multiplied by a -4, then we would need to flip the symbol, and sometimes you'll have to do that. Multiply by a negative to get the x by itself, and then when you do that, then you need to multiply the symbol. All right, a little different here. Just adding steps as we move along. Absolute value of x minus 5 is less than or equal to 3. Absolute value of x minus 5 is less than or equal to 3.
Both sides, like making a positive 3 and a negative 3?
Yeah, both sides. Well, both sides of what?
I mean, like, when we do it, do we need to make it, the first problem needs to be, leave it the same, and the second problem needs to be like x minus 5 is less than or equal to -3?
Yes, right. The part that's inside the absolute value, we treat it as one thing. And because you can't take the absolute value of pieces, that -5 is going to stay -5. Y'all listen to me. That's a common mistake. People think that that becomes x plus 5 because the absolute value makes things positive. But the absolute value affects the whole expression, not pieces of the expression. Right? You can't take the square. It's just like canceling a term. You can't cancel a term. You can only cancel factors. So we treat that as one thing.
Could we make
Jay?
5 positive if we made 3 negative?
No, you cannot make the 5. You cannot change the sign of what's inside the absolute value. They could both be negative, and you're still not going to change the sign. Okay? That changes the output of the problem, or the result of the problem. So, letter A, is it going to be an AND problem or an OR problem? And, right? So x minus 5 is less than or equal to 3. And, the most important word on the page, it has to be in your work. What's the second equation going to be?
X minus 5 is
Greater than or equal to -3. Flip the symbol, change the sign. This is very similar to the equations. We just have to remember flip the symbol and change the sign, and we have to remember and OR. So when you solve those, what do you get on the left? X is
the
less than or equal to 8, and
x is greater than or equal to 2.
all right, and graph, always graph, always graph. As a matter of fact, your answer is your graph for me at this point. Now, we're not going to assume that it's everything in between 2 and 8. We're going to graph it and make sure it works that way. Less than or equal to 8 is a closed circle and shade to the left. Greater than or equal to 2 is a closed circle and shade to the right. And they do overlap each other between 2 and 8. So there's my solution. Now, when you get to algebra 2, that's 2 to 8 in brackets. So x is an element of this interval. Yeah, Brent? You good? Okay, all right. The second problem, letter B there, is that going to be an AND or an OR? Greater is OR, right?
Or tor.
Greater. Greater is OR, but only when we're dealing with absolute value inequalities. Here's the danger, and my college algebra students get this wrong all the time. After we do this lesson, they'll take a simple problem like this and change it into 2 problems. Why wouldn't I do that? Because it's not an absolute value. Only absolute value problems split into 2 equations. So that's not right. We've never split a problem that doesn't have absolute values. So that's a common point of confusion. So greater is or. So I know I'm dealing with an or problem here. So x plus 7 is greater than 3, or x plus 7 is less than negative 3. Flip the symbol, change the sign. Subtracting 7 on the left gives us x is greater than negative 4. Subtracting 7 on the right gives us x is less than negative 10. How do you graph or problems? How do you graph or problems? Because it is a union, we just graph them together. We just join the two graphs. That's negative 10, which is there in relation to negative 4. Less than negative 10, we shade to the left. Greater than negative 4, we shade to the right. What number is right in between these two numbers? What's the midpoint of negative 10 and 4? Negative 7 is correct. You think it has anything to do with that? Now, what is x plus 7? What is the solution of x plus 7 equals 0?
X equals negative 7.
X equals negative 7. So the 0 of that thing inside is key. What were the numbers in letter A? I forgot what the solution was. Do what? The solution here. 2 and 8. And it was everything in between them, right? What's the midpoint there? 5. You think it has anything to do with that? Yeah?
Would it be a negative 5?
No. It's where x minus 5 is equal to 0. It's ground zero, if you will. Right? Ground zero is the midpoint, you know, our dividing point. And when we start talking about optimal, that's the optimal. That's the ideal. The distance between x and negative 5 is what we're talking about there. We need that distance to be, in this case, less than or equal to 3. And that would mean those numbers need to be between 2 and 8. Which is, look, 3 units from 5 is 2 in that direction. 3 units that direction is 8. So our distance is within 3. Our distance from positive 5 is within 3. Here our distance from 7 is more than 3. Right? Well, distance from 7 is more than 3 means we had to be outside of negative whatever it was and negative whatever it was. I forget those numbers. Yeah, Jay?
Will that what's in the middle thing ever not apply to the equation?
No, it'll always apply. Ground zero will always apply. Cool. Now, but if I threw in something like this, 2x plus 1, then the 0 of that one would be what? What makes 2x plus 1 equal 0? Negative 1/2 is going to be the splitting point for that one. Okay? So, but yes, the zeros will always be important. All right, here we go. Special cases. Y'all ready? Special cases. Now, how do I know these are going to be special cases? Just from looking at the problems. Because they're absolute values that deal with, or will deal with, negatives. So, letter A here, what would I do first? You subtract 6 from both sides, and when you do that, you get absolute value of x is less than or equal to negative 2. Now, what did I tell you? What did I tell you? Absolute values will always split into two problems, right? So, x is less than or equal to negative 2, less than is, and x is greater than or equal to positive 2. Tell me a number that makes that statement true. Is it possible for a number to be less than negative 2 and Greater than positive 2?
No.
No.
It's not possible, right? Now this is one of those instances where if you continue on this problem and you do what you should do on an and problem, we have negative 2 and we have positive 2, you cannot assume that you just shade in between those two numbers just because it's an and problem. We're looking for intersection, right? Less than or equal to negative 2 is this. Greater than or equal to positive 2 is this. Do we have any intersection?
No.
We do not have any
That
intersection.
means it can't be
This
a
is
number.
no solutions. Now, let's talk about how you could reason your way through this just when you get to this step right here. We get to that step right there. What do we know about the distance from 0 here? It can't be negative. It's positive, right? Can something that is positive be less than something that is negative? No. This is nonsense. Positive can't be less than negative. And so this has no solutions. You don't have to work through these processes to do that. But you should be careful. All right? It's okay if you do. The process will give you the correct answer. When you're dealing with an equation that's equal to a negative, if you split it into two equations, you get two incorrect answers. Okay, so you're not safe to split an equation that's equal to a negative number, absolute value equation equal to a negative, but you are always safe to split an absolute value inequality. It will lead you to the correct answer. That's why always was in quotes earlier in the lesson. It's literally always. You don't have to do it, but it's always safe to do it. Similarly, on the right side, example B, what would we do here? Subtract 6 from both sides. And that gives us absolute value of x is greater than negative 5.
Isn't that an OR problem as well?
It is an OR problem, right? So what would the two OR problems be?
X is greater than negative 5 and x is less than 5.
Not and.
Or x is less than 5.
X is less than 5. Now we're just going to continue through the process. How do you graph an OR problem? You graph them right on top of each other. You do not assume that they're going to always open out. Negative 5, positive 5. What's greater than 5?
6.
The shade's this way, right? Greater than negative 5, excuse me. What about less than 5? The shade's
That way.
this way. What did we shade?
Everything.
Everything. We shaded the whole real number line.
So all real
So our
numbers.
solution is all real numbers. Now think back to, let's go back to this step right here.
Hold on. What if the, oh yeah, because negative 6 can't be answered.
Think back to this step right here. All right? What do we know about the absolute value of x? It's always positive. When is a positive number greater than a negative number? Always, right? Anytime something is always true, then our answer is going to be all real numbers. Okay, so you have to be careful with the negatives when you're doing absolute values, but not as careful as with equations. If you work them through, if you split them and work them through, you still get the correct answer graphically. All right? Here we go. Word problem. A poll finds that candidate Garcia is favored by 46% of the voters surveyed, and Jackson is favored by 44%. The poll has an accuracy of plus or minus 3. Write an absolute value inequality to show the true percentage of voters for Garcia. For Garcia. All right, so we're going to ignore Jackson. No offense to the two Jacksons that are actually in this room. We're not going to ignore you guys. We're dealing with Garcia. The actual percentage of voters is within 3, plus or minus. All right? Is that going to be greater than or less than 3?
Both. Greater than or less than 3, right? Plus or minus.
So it's less than positive 3 and greater than negative 3. It's plus or minus 3. So that's less than or equal to 3% difference. So the actual minus the optimal is less than or equal to 3. And this goes back to what we dealt with absolute value equations, right? Y'all remember that? Our actual minus the optimal is equal to, what do we call that? The tolerance, right?
Right, how did you get less than or equal to?
It's within 3 either way. So the distance between, so what would the upper boundary be? If the actual is 46, what would the upper boundary be?
49.
49, and the lower boundary would be 43. So that's an and problem. It's less than. It's between 43 and 46. This goes back to this, guys. This is an important concept for tolerances. You'll see this a lot in physics. You'll see a lot in chemistry. Actual minus optimal, the distance between those two things is equal to the tolerance. Well, the tolerance of this particular survey is plus or minus 3. So the distance is within 3 of it.
So, like, problems like this are always going to be less than or equal to?
Yes. 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 So we could talk about a company manufacturing bolts. And these bolts, the ideal bolt is 50 centimeters or 50 millimeters makes more sense. 50 centimeters, that would be a big bolt. 50 millimeters is the bolt. That's still a large bolt. But if we had 50 millimeters of this bolt, right, and it could be within 0.1, right? So the largest it could be is 50.1, and the smallest it could be would be 49.9. Right, so the actual size of the bolt minus the optimal size of the bolt would be less than or equal to 0.1. Actual minus optimal is less than or equal to the tolerance. And I can't think of very many applications right off the top of my head where greater than or equal to would be in play. Because tolerances, we're usually trying to narrow down something, right? Trying to pinpoint a specific value. We're not trying to get out away from it. We're trying to narrow it down. All right. I think that your assignment should be on the next screen. Look, we're in the 600s, guys. We're going to finish a textbook.
Have you ever?
Isn't that crazy?
I don't think I've ever finished a math test before.
I've never finished one either.
We all knew we were